Good afternoon. My name is Cheyenne Smeaton, and I'm here to present to you the Patent Office. What we're going to talk about today is the Haber process. Now, what is the Haber process? Well, this process was created by a man named Fritz Haber. He was a German Jewish chemist, and this was created in the 20th century during World War I. He did reside in Germany. In 1905, he solved the sought-out answer, which chemists had been looking for a very long time, which was how to fix nitrogen from air. He understood that by using high pressure and a catalyst, he was able to find this answer. So the high pressure and the catalyst was able to transfer nitrogen gas and hydrogen gas into ammonia. Once the process was recognized, it was scaled up by a chemist named Carl Bosch. So this process was scaled up so that it could be used in a larger process and for many more things. When Carl Bosch came into the picture, it was then called the Haber-Bosch process. It is still called the Haber-Bosch process till this day. Many people even now consider this an essential part in the technological advances of the 20th century. This breakthrough did allow for mass production of agricultural fertilizers and also led to a large growth of crops for people to eat. So especially during the 20th century, where we had many things going on and a lot of people were unable to eat, the depression, finances, everything was kind of going in a downward spiral. This process was able to kind of break them out of this process, and it was a huge help for the agricultural fertilizers, and that led to many more people being able to eat because of the overproduction of the crops. Le Chatelier's principle. He was a chemist born in Paris, France on October 8, 1850. This principle recognized the dynamic equilibrium that is interrupted by the changing conditions. And what that means is that it is used in the Haber process for industrial purposes like ammonia, nitrogen gas, and hydrogen gas. Synthesizing. When synthesizing ammonia in particular, it increases the reactant's concentrations, and it will transition the equilibrium into making more products. When increasing the product's concentration, the reaction will be able to produce more reactants. Now, on the opposite side, when decreasing the reactants, it favors reactants. So when we decrease products of the Le Chatelier's principle, for change or pressure must occur when the substance is in a gaseous state. It can only occur when the substance is in a gaseous state. A catalyst, what that does is increase the reaction of speed. By adding a catalyst, it has no impact on the equilibrium's positioning. When catalysts are speeding up the rates of both the forward and reverse reactions, the rates will remain equal because they are changing at the same amount. Le Chatelier's principle and the conditions that favor the forward reaction. The conditions that favored the forward reaction is that the change in equilibrium in every situation is either favoring the forward or reverse reactions. So in order to take a look further into this, when a forward reaction is favored, the concentration of products will increase, while the concentrations of reactants will decrease. It is essential to know whether the forward reaction is exothermic or endothermic, because this will change the answer. The reaction was to be exothermic, then the reverse reaction would be endothermic, and vice versa. So if the reaction was endothermic, then it would be exothermic for the reverse reaction. A catalyst also increases the reaction of speed, like we talked about. By adding a catalyst, like we said, it has no impact on the equilibrium positioning, and due to these catalysts speeding up the rates of both the forward and reverse reactions, it will remain equal, and that is because it is changing by the same amount. Temperature and pressure conditions, this reaction is typically carried out. The high temperatures and low pressure rates versus low temperatures and high pressure rates can affect the system. The change in temperature Changes in the concentration of the reactants or products of a reaction shift the position of the equilibrium. They do not change the equilibrium constant for the reaction. By raising the temperature of the system, it is the same as to adding additional product to the system. The equilibrium constant therefore decreases with increasing temperature. Now, the change in pressure is that an increase in the total pressure on the system is typically what occurs. The reaction will then shift in the direction that minimized the effect of this stress. The reaction shifted toward the products because this reduces the number of particles in the gas, thereby decreasing the total pressure on the system, as shown in the figure below, which the figure below did not upload for some reason. I couldn't get it to actually stay on the slide, so what was condoned in that figure below is just that you could see the number of particles in the gas and that it was decreasing the total pressure on the system. This is a great example as to what that would have been, is this picture on the right hand side. A catalyst most commonly used for in this reaction is increasing the reaction of speed. Adding a catalyst, again, has no impact on the equilibrium's positioning. Catalysts will speed up the rates of both the forward and reverse reactions, and they will remain the same and equal because they are changing by the same amount. Like we stated before, this is very important to understand because this is how Le Chatelier's principle favors in the Haber-Bosch's process. Lastly, what are the environmental impacts of the Haber process, to include approaches being taken to reduce the use and environmental impacts of such fertilizers created by this process. Global manufacturing of ammonia responsible for 1.2% of anthropogenic carbon dioxide emissions. The majority of the carbon dioxide emissions is from the Haber-Bosch process and are results on the ability for use of methane as feedstocks rather than fuel. Energy losses are also determined and bound by the steam turbine compressions, which are used to manipulate high-pressure synthesis and reform the reactions to enable the ammonia refrigeration compressor. It uses about 2% of the world's total energy. And for nitrogen pollution, there is an overgrowth of algae. There is a massive amount of fish deaths due to the overgrowth of algae. When algae overgrowths, it takes up so much oxygen within the water that it is not sustainable for fish, and it is also not sustainable for aquaculture because the aquaculture cannot grow due to not being able to undergo photosynthesis. And the fish can't live in the water because the oxygen levels are so low. Those are the environmental impacts of the Haber process, now called the Haber-Bosch process. Current research exploring a sustainable electrochemical method to drive this chemical reaction is the study conducted by Texas A&M University. They realized that 2 carbon dioxide molecules are made for every molecule of ammonia produced. This contributes to excess carbon dioxide in the atmosphere. It is produced using the electrochemical nitrogen reduction reaction. This is what they want to propose to use instead. So the benefits of using this electrochemical method is by using the water to provide protons and the ability to produce ammonia at ambient temperatures and pressure. This will require lower amounts of energy, and it will be less costly and more environmentally friendly than the Haber-Bosch process. How the electrochemical methods work is it uses an electrocatalyst. The nitrogen must bound to the surface and break apart to produce ammonia. In this certain study by Texas A&M University, they used amexine, a titanium nitride, which was used as the electrocatalyst. The nitrogen is already in its structure, which allows for more efficient ammonia formulation. So that is the difference. The difference is the electrocatalyst, which in this case is the amexine, is a titanium nitride. And that titanium nitride has nitrogen already in the structure, which is the difference. The Department of Energy, the results of this study is kind of up in the air only because the Department of Energy has set a goal of a selective of 60%. So that means that researchers have to reach 60%, which is more than half, before anything can be done to change the process. And researchers at this point have only reached 20%. But they do have plans and methods to try to reach that 60% in the future. And lastly, this is my works cited page, and it is the similar citations to what was in my annotations and my bibliography. I hope everybody has a great semester, and good luck. Thank you.